Okay, so at this point, we are going to switch our focus more towards the synthetic aperture radar data sets themselves. I don't have time to go into a very deep dive on the synthetic aperture radar data sets, but I do want to give a brief introduction to help you understand what this data set is and how it's collected. At the end of my presentation, these slides will be linked, as Cindy mentioned, on the website. And the last two slides are lists of resources. So if you're interested in learning more, the first of those two resource slides includes a number of links to webinars. Alaska Satellite Facility's chief scientist also teaches a massive open online course in SAR, and a new iteration of that has just started this September. And so if you're interested in doing a deeper dive into SAR without having to commit to a full semester of a class, I do recommend checking out that opportunity. So a few key components of the data acquisition for synthetic aperture radar. First of all, SAR makes use of the microwave range of the electromagnetic spectrum. So this is a longer wavelength than infrared, but it's shorter than radio waves. SAR uses an active imaging system, so it's creating its own illumination. There's a very controlled pulse that's sent down from the sensor to the Earth, and only the returns of that controlled signal are measured. SAR makes use of a side-looking geometry, so it's always imaging at an oblique angle to the Earth. And this is necessary in order to process the data and understand it correctly, but it does mean that there are distortions that are inherent to SAR data sets that you need to be aware of. And in many cases, you'll need to correct for them as you use the data for analysis. People often wonder what exactly is synthetic about SAR. Sorry. Essentially, to get a reasonable resolution on the Earth's surface, you would require an extremely long antenna because the signal has to travel so far, especially from a spaceborne antenna. The antenna would have to be so long that it's physically impossible, essentially, to be able to get a reasonable resolution on the Earth's surface if you're flying like a 5-kilometer long antenna, for example. So synthetic aperture radar makes use of the motion of the sensor as a proxy for that longer antenna. So rather than having a huge antenna, it's collecting data along a path, and then post-processing focuses that data to give you a higher resolution without having to have that super long antenna. Some of the benefits of SAR, including the fact that it can penetrate cloud cover. This gives SAR the ability to image the Earth's surface through clouds or heavy smoke. And this is particularly important when imaging the Earth's surface during natural disasters like hurricanes or wildfires, or if you're trying to monitor surface processes in areas that are prone to frequent cloud cover. So areas in the rainforest, for example, or Southwest Alaska, where there are just very few cloud-free days that allow monitoring with more optical data sets. SAR is not sensitive to light availability because it is an active sensor. It creates its own illumination, so there's no need to time orbits with the presence of sunlight. With the addition of SAR to satellite platforms, there's now global coverage with SAR data, and many of the constellations provide very frequent and regular imaging on very stable orbits. So the data can be collected from very close to each other on repeat passes so that you can monitor the surface properties from pretty much the exact same place in space. SAR can collect data using different polarizations, and these different polarizations tell you different things about the characteristics of the Earth's surface. Some sensors are only single pole sensors, which means that they send out the signal in a polarization and can only measure returns that are still in that same polarization. So if the primary polarization is vertical, the signal is sent out in a vertical orientation, and only the returns in that same polarization are measured, giving you the VV returns. Similarly, if it's sent out in a horizontal polarization, you can only receive the horizontal returns, or the HH. Many sensors are dual pole sensors, which means that they still only send out in one polarization, but they can receive both the copolarized and the cross-polarized returns. So if it's sent out in a vertical orientation, it receives those VV returns, but also the VH returns. It can measure any of the signal that has been cross-polarized while it's interacting with the Earth's surface. Similarly with the horizontal, if it's a horizontal send, you get both the HH and the HV returns. There are some sensors that are quad pole sensors, which give you the full suite of polarimetric measurements. And that's a very powerful data set. It helps you really interpret what's going on the Earth's surface in a very complex way. But it is a very large amount of data. So in quad pole sensors, it's sending out both in horizontal and vertical and receiving both in horizontal and vertical. So not only is that a lot of information that has to be sent out by the sensor, which takes a lot of energy, it also is a lot of data that has to be downlinked and processed. So usually there are trade-offs when there is a quad pole data set. Either the swath has to be narrower or the frequency of collection is less. So in many cases, if there is a quad pole sensor, it's probably not providing global quad pole data sets. It may just be acquiring certain areas with that quad pole mode. SAR is very sensitive to small changes in the elevation of Earth's surface, which makes it an excellent tool for monitoring surface deformation from processes such as earthquakes and volcanoes, or really anything that changes the height of the Earth's surface. The SAR data sets are composed of two different components. There's amplitude and phase. The amplitude is the amount of the signal that returns to the sensor. So there's a pulse that's sent out, and how much of that actually makes it back is the radar backscatter. The backscatter is impacted by a number of different things, including the polarization of the signal. So VV polarization, for example, is very sensitive to surface roughness. So if the surface is rough, you'll get higher returns in the VV backscatter, and smooth surfaces will have lower returns. The VH polarization is more sensitive to volume scattering. And a common volume scatterer on Earth is a vegetation canopy. So if it's interacting with a forest canopy, you'll get much higher returns in the VH than if you're imaging over a bare surface or if there's very little vegetation present. The dielectric properties of the scatterers on the Earth's surface also impact the amount of backscatter that can be returned to the sensor. So the dielectric properties essentially describe the permittivity of an object to these signals. So targets with higher dielectric properties are better at reflecting the signal back. And so you would expect that there would be higher backscatter from objects that have high dielectric properties. Whereas objects with low dielectric properties are able to absorb more of that signal. And so there's generally lower backscatter from those low dielectric property scatterers. That said, there's kind of a complex interaction that goes on between things like surface roughness or volume scattering and the dielectric constant. If we look at the images on the right side of the screen, you can see that these are collected over an area on the north slope of Alaska, which is very flat and open, and there are lots and lots of small lakes. If we look at the top left image, that's collected with VV polarization on a calm day. And you can see that the lakes are very dark in the image, that they're very easy to differentiate from the surrounding tundra. And that's because you have these smooth surfaces, so the roughness is very low, and fresh water has a high dielectric constant. So the signal is coming in from that oblique angle, hitting that nice smooth surface and bouncing off very effectively, but it's all bouncing off away from the direction that the signal came from. So very little, if any, of that backscatter actually gets directed back towards the sensor to be measured. If we look at that same area on a windy day, up in the right corner, you can see that the VV returns are very different. It's almost impossible to distinguish between the lakes and the surrounding tundra just visually. And that's because the wind has roughened those surfaces of the lakes, and the signal still reflects very effectively off the surface. But because of the wave angles, some of that signal is now directed back towards the sensor. So it has much higher backscatter on those windy days. If we look at the VH returns on the bottom, you can see that there's not nearly as much impact of the wind when you're looking at the VH returns. And that's because even though the surface is roughened due to the wind, it's still essentially a surface. It's not creating a volume or a complex sort of layer of things like you would see in a forest, which has a lot of leaves and stems and trunks that can really redirect that signal and potentially depolarize it. In this case, it's any of the returns that are coming back from that water are generally still going to be in the vertical polarization. So another thing to be aware of when working with SAR data is that different SAR sensors use different bands. So they may have different wavelengths. And the wavelength of the signal impacts how well it penetrates into either a volume scatter like a canopy or into a surface like a soil surface. So a C-band sensor has a wavelength of about 5.5 or 6 centimeters. So if you have a dense forest canopy with lots of leaves and deciduous trees that have big leaves, that signal, which only has a 6 centimeter wavelength, will not be able to penetrate very far into that canopy before it's scattered back. So most of the information that you're getting returned is going to be indicative of the conditions in the canopy. Whereas with an L-band sensor, those are more in the order of 25 centimeters, which is much longer, and it has the chance to penetrate further down into that canopy and interact with either the canopy lower down or the tree trunks themselves, or potentially even the forest floor. So, and the same thing holds if you're looking at bare soil. So returns from a C-band sensor will be more indicative of the conditions in that top layer of the soil, the surface soil, rather than deeper down, whereas the L-band may be giving you more information about the root area of the soil. So having access to different bands actually gives you a much more complex picture of what's going on and can be really useful. So if you have data sets that were collected with different bands, you can consider both of them when you're trying to understand the dynamics that are occurring. But you also have to be careful because these data sets are not comparable. So if you're looking at data sets that were collected with different sensors, you want to be careful that they were collected with the same wavelength. Because if you're comparing C-band data to L-band data, it's not an equal comparison. It's really telling you different information. So it's always important to be aware of the wavelength of the data set that you're working with. In order to make amplitude data useful, in most cases, you'll need to perform radiometric terrain correction. As I mentioned before, that side-looking approach to imaging creates distortions that will make the image not line up with other imagery if you're trying to compare. So if we look at the image on the left, you can see that the mountains outside of Juneau, Alaska all look kind of squashed over and have a bright leading edge. And that's because of the angles involved. So if the mountain slope is at the correct angle to interact with the incoming signal, you may actually have returns coming back from the top of the mountain at about the same time as from the bottom of the mountain. So the sensor interprets that as all coming back from the same place on Earth. The time is all the same. This is when they all returned. So it's considered to be sort of one area. And so it compresses that foreslope of the mountain into one kind of narrow band. And because it thinks it's all coming from one area, the backscatter looks much brighter than is actually true, because what you've got are all these scatterers from the entire mountain slope all contributing to that one return, when really there's a lot of area that's covered. So radiometric terrain correction uses a digital elevation model to not only move the topographic features into place, but also to normalize that radar backscatter based on the actual surface area that's contributing to that signal. So if you look at the image on the right, you can see that the mountains are more where you would expect them if you're looking down from above. And also the radiometric returns from the front slope and the back slope are much more similar. It's been normalized in that way, so you don't get that compression effect. And as Cindy mentioned, Africa will be discussing radiometric terrain corrected products in much more detail in the final tutorial of the day. So the other component of SAR data is the phase. And the phase is the location of the wave along its cycle when it returns to the sensor. So there's a signal, a controlled pulse that's sent down, it travels to the Earth's surface, it interacts with the scatterers and comes back to the sensor to be measured. So we get the amplitude, how much of that returns, but we also know where it is along its wave cycle, or the phase. So if you were to collect an image, you've got the phase information, then you orbit around, come back 12 days later, take an image from the exact same place in space. If nothing has changed on the Earth's surface, you would expect that the signal would be sent down, it would interact with the surface, come back, and the phase measurement would be the same as it was the last time. If, however, there's been some sort of surface displacement, if there's a volcano or an earthquake that is either that has caused the Earth to move upwards or closer to the sensor, that signal doesn't have to travel as far. So the phase will be less far along in the wave cycle than it was in the previous acquisition. Whereas if it's subsided or moved away from the sensor, that the signal has to travel longer. So the phase will be further along in the wave cycle the next time it's measured. So comparing these two phase measurements from different acquisitions is the basis of SAR interferometry. So you need two acquisitions that you can compare to see if there's been surface deformation occurring and how much. In order to get this information, you have to process the data to an interferogram. And we'll be, in the tutorial after the break, we'll be going through the INSAR products a little bit more. But in general, if you look at the fringe pattern, the fringes that are very close together indicate regions of higher deformation, whereas fringes that are wider apart indicate that the ground has not moved as much.